For this lecture, we're going to talk about linear regression. Now, linear regression is a model we're going to use for regression. So we're supervised machine learning, particularly regression. And as the name implies, linear regression assumes there is a linear relationship between the features, the data that you have, the characteristics for your observations you have, with the value you want to predict, the labels, the y. Now, the thing about linear regression is that it's a rather simple model. And yes, a rather simple model isn't going to perform so great compared to other complicated models, compared to more complicated models. But working with a linear regression, a rather simple model, is a great model to first talk about. Because some of the questions we're going to ask for this model, we can go and ask for more complicated models. So let's get an understanding of how this model works, to get a feel for it, and go ahead and take this line of thinking and this approach when we discuss more complicated models. We'll see some common themes be brought up when we delve into other models. Now, the nice thing about linear regression is that you can write out the functional form for the model. Let's just consider a situation in which we only have one feature in our data set, just x1. What linear regression is saying is that the predictive value y is equal to beta naught, an intercept, plus beta 1 times x of 1. And what we're trying to do, you can think what we're trying to do is you're trying to figure out what are good values for these model parameters. How should we set these model parameters such that we have a model that best fits our data? We'll discuss that later on in this lecture. For this notebook, we're going to look at gas consumption data. So let's go ahead and load the data set, dump it to pandas. Right, make sure I run these two blocks there. Okay, so there we have our data set. So we have gas consumption as for different values, different features like the tax, the income, some highway number, and drivers, which I believe is a percentage of the population. Right, let's go ahead and just only plot one of these features. Let's go ahead and see how the value we're trying to predict varies with the percent of population that is driving. So we do that there. So we see our graph here, our simple graph. And notice there's a general trend that we see in when we plot our data. Generally, as this percentage increases, the gas consumption is also going to increase. There is a trend. So the question is, where should we draw a line that's going to best fit this data? Where should I position it? What slope should it have and what intercept should I have that's going to best fit the data? Now I can go ahead and manually do this. That's what we're going to do here in this block. We're going to plot two graphs, two different options for our line, a blue one and a red one. Sorry, a green and a red one. At least for me, it's very difficult to visualize this, to look at this and decide which one is the better line to use. Should we use the green one or should we use the red one? At least for me, it's not easy to decide which one to use. So let's come up with a more sophisticated approach, a more systematic approach to decide which line should we use, or maybe some other line will be better. Go about figuring out a more systematic approach. So what we got to do is we got to talk about a metric of interest, and to derive some measure of error in our model. Either of these two lines will have error. One of them has less error than the other, so we should go ahead and use the model that has the least error. So I'm talking about error, so let's be more concrete what we mean by error. So what we're going to do here is we're going to define error as simply the true value, the value we're trying to predict for a given observation, minus the model's output for that observation. So y represents the true value. This here that I'm highlighting represents the model output. Remember, if we go back up above with linear regression, we're saying that the predicted values are beta naught plus beta 1 times x of 1. That's what the model is going to predict, given an intercept, given a slope. The predicted value. So the deviation from the true value is a measure of error, is our error. We want this error to be as small as possible. And specifically, what we're going to do is we're going to sum the square of all the errors for our observations, so we can define the mean squared error. So the name applies. We're summing up all our error messages, or all our errors, the square of the errors, and dividing by n. the number of observations, to derive this metric here. So we're going to try to find our goal with linear regression. What linear regression is trying to do is figure out how should we set beta naught? How should we set beta 1? How should we set these model parameters such that we're going to have the lowest mean squared error from our training set? Since this is the objective, our objective is to reduce the mean squared error. It's often called the objective function, the cost function, or the loss function. This is the function. This is what we're trying to minimize when we train the model. And this is for linear regression. Other models will have different cost functions, but the idea is still the same. For these models, there is some objective. There is some penalty, some cost it's trying to reduce. And it's going to look for model coefficients, model parameters that is going to reduce this cost function, the minimum of this cost function. Okay, so let's go ahead and use the linear regression in scikit-learn. So we're going to import that, our linear regression class. Let's create a linear regression model. So we do there. And we're going to set this keyword argument fit intercept to true. In fact, this should be the default. But let's be explicit and set the intercept to true. In fact, we have the capability of setting this to false. And if we do set it to false, it's going to fit the data to the model, but it's not going to include the intercept. In other words, if I set it to false, what I'll do is just y equals beta 1 x of 1. All right, it's a good time to look at some documentation. Fit intercept, Boolean option, default true, whether to calculate the intercept of the model. All right. So since the default is true, we don't have to be explicit, but let's just, for demonstration purposes, set it to true. Okay, and we're going to fit with our data set to only include the drivers field we're trying to predict on the gas consumption. Let's go ahead and plot the data. And let's also use our model to make predictions. So that's what we're going to go ahead and do in this block in this cell here. In this block here, we're going to use the linspace function to generate a linear space from point 4 to point 8. Remember, we're going to reshape it. Scikit-learn wants the data, the feature matrix to be 2 dimensions, has rows and columns. So we're going to make sure we reshape the data. And we're going to pass this created value, this created matrix, into the predict method of our trained model. So when we call the fit method, what do you think is happening when we call the fit method? What do you think is happening underneath the hood in scikit-learn when we invoked fit? Well, when we use the fit method, scikit-learn is trying to figure out what are the good beta coefficients to use to best fit, best draw a line, best put a line through our data set. We'll talk about exactly how it's finding that out, what method, what algorithm it's using to figure out the best set of beta coefficient values, but that's what's happening underneath the hood. Okay, and let's see how well our model performs. So we have in black, the line in black is the predictive values from our trained model. So this line in black is the line that's going to reduce the mean squared error the most compared to any other lines we can draw through the data set. So it's better than the red line and the green line. So we trained our model, and let's talk about how we can look up the model coefficients. Remember, in this model here is just one variable, beta 1 and beta naught. So beta naught is the intercept. You can call beta 1 as our slope. Let's say we want to know what these values are, how we go about inspecting these values. Well, notice those values, we only know them after we fit the model. So we're going to talk about that convention that scikit-learn uses. in which attributes of a model that are determined after the fitting process are going to end in an underscore. In fact, it's just called intercept underscore will return to us the scalar value of the intercept, and the coef attribute, also ends in underscore, will return a numpy array of all the model coefficients. Notice that we only have one model coefficient as opposed to the intercept. This numpy array will just be of shape 1, so let's just pull out the 0 index. And there it is. So there is our slope, and there is our intercept. And as before, if you want to know what other attributes you have, by all means take a look at the documentation. I'm going to do that right there. There's the attributes. We'll tell you what data type they'll come out of and some additional information.